Let's continue looking at key commands that are important throughout your life as a Linux engineer. Now, when your system boots, there are a number of messages that are logged that are not captured by syslog. These can be exposed using the dmesg command. So another important command is dmesg. The kernel logs to a file in varlog named dmesg. It contains the contents of the kernel's ring buffer. So let's just note kernels or kernel ring buffer. These are items that are logged by the kernel before syslog becomes available. So pre-syslog, or whatever invocation of syslog you're running, rsyslog, syslog-ng, etc. Default in Red Hat Enterprise Linux is rsyslog, which functions like syslog. So dmesg is that command, and it's located in varlog. Let's take a look at the shell. We should find a root shell because the contents of log items pertaining to the kernel should be restricted. Let's take a look by navigating in varlog, and there we see dmesg. Let's examine the contents of the metadata or permissions. It's actually readable by all users, so that means we could read the content since it pertains to peripherals and wouldn't expose any personal data. So dmesg is the file in varlog, and you can expose its contents using the dmesg command. It will dump all of the messages picked up by the kernel since the last boot. The file is automatically rotated, and if you use a pipe to send the output into less, you'll see it one page full at a time. It includes everything from the perspective of the kernel, the hardware that was detected, meaning the type of processor, the amount of memory, if there were any connected peripherals, storage devices. So everything pertaining to the physically connected items. For example, the fact that the box has 2 gigs of memory was detected. And it also includes one important item that I reference dmesg often for, and that is how the kernel was invoked. So let's just note, also contains how the most recent invocation of the kernel took place. In other words, the command line that was used to invoke the kernel. This becomes important when you attempt to debug how your system came to be, in the event that there's a problem, of course. If we run dmesg in pipe in search of command line, and that I option is a case insensitive search on grep, there's a line named kernel or that begins with kernel command line. It includes a string that was sent to the kernel to start the current kernel, including anything that we may tap on to the end of it. So notice the number 4, which means that this system started in the 4th run level. Indeed, we're in run level number 4. This was for making changes to the config file. We can update this right now by modifying the grub.conf file, but let's just copy and paste this verse into our notes to indicate one way in which you may extract information from the file. So this extracts or returns current kernel command line. And to adjust it to run level number 5, we can modify using the nano editor, which is another command, etc grub.conf, which is really symbolically linked into the boot directory. Navigating to the kernel line and removing run level 4 will cause the system to boot in the default run level specified in etc init tab, as mentioned during the init section. So notice that init tab instructs the system to boot in run level 5, but there was an override supplied to the kernel via grub that I had placed in there just to throw things off a bit. So dmesg shows you that information, and query it from time to time. You'll see messages pertaining to all sorts of physically connected devices, including printers. For example, let's say your printer is out of paper that's connected. That may be a message, that demessage that the kernel may log to this file. Certainly networking information, the speed at which the interfaces or interface connected to the wire, all of that will be, of course, registered. So we're connected at fast Ethernet speed, etc. So demessage is another one in your toolbox that you should have. Let's keep going on some more simple commands. Head and tail. These are two converses that allow us to parse specific portions of textual documents. So returns header and footer of text documents. And of course, it's customizable. So for example, when we take a look at the contents of varlog messages, it's a bit plentiful. Supposing we wanted to see just the first n number of items, using head and the file name, that will return n number of items. You can pipe the output into the word count program, and you see that head defaults to showing you 10 lines. These are the first 10 lines from the document as far as head is concerned. So that shows you how to extract the first 10 lines. Head varlog messages returns first 10 lines, and conversely, tail varlog messages returns last 10 lines. It's often desirable to see just the last block of input to a file. So changing this to tail, I'm using Control-A to jump around, Control-E. These are the last 10 lines. Both utilities are customizable, so you can indicate the number of lines. For example, show me the first line from messages, or show me the last line, or n number of lines. You can go beyond 10, for example, so show me the first 19 lines, etc. Detection of the CPU, etc. So head and tail are important because one of the primary things that you do as a Linux administrator is to deal with globs and globs of text files. And you have to be able to parse those files in a sensible and timely fashion. Another command that's of interest is the file command. This returns the type of data stored in a file. And it does so using its magic file. It's able to discern, and usually quite accurately, the type of file based on its magic database. And you can just man file to get more information about how file does its work. And if you query the package that file is a part of, you'll see that it has its magic file, and it is able to compare the strings that it finds in the header of files to make a guess as to the MIME type or type of file that it is interrogating. So this is the default compile list of magic files, or magic entries that is, and this is a directory containing magic files. So you can modify that particular path. Now this is a binary file, so it doesn't show us much useful information. Let's do a user share miss magic, and the magic file contains, this is a text file, various strings that pertain to different types. For example, let's grep PDF from user share miss magic, and in here we'll see a string that pertains to how this is able to determine if something is PDF. So file will help you to figure that out. Now let's get a sense for different file types. Let's navigate into the user Linux CBT's home directory and see some of the files that are there. We'll do a file against *text, and it returns that these are ASCII text files that are formatted for Unix and Linux platforms. For binary files, for example, let's do a which ls. ls is in bin, so file bin ls will return that it's an executable for the x86 platform for GNU Linux 2.6. So file is a very handy program, especially when scripting and having to make decisions based on the contents of a file at any particular time. Another useful command is ps. ps lists processes that are currently running. By default, if you're logged in as a non-privileged user, it shows you the processes of the currently logged in user. So in this this particular shell, sudo terminal 0 bash is the process that was running initially, and ps was executed after. So let's just note ps lists processes for currently or current user when run as a non-privileged user. But ps can be extended with a number of options, including but not limited to ef or aux, to show additional fields and processes of other users on the system. Scrolling towards the top, which can be quite cumbersome, you'll see the columns that have been returned with aux. To fix this output, we can pipe the output to less, and then we see the columns at the top of the page. So these processes all belong to root. PID1 we know is init. That was the command that was run. The percentage of CPU and memory that's in use, currently none, because init spawns other processes and then sits in the background waiting for various events to occur, such as a shutdown or Control-Alt-Delete sequence, and various other fields. And as we scroll through, we'll see processes that belong to different users, including the user Linux CBT. You can examine the process listing for a specific user if you'd like. Just run ps with the help option. You'll see the myriad options that may be used to return specific pieces of information. I tend to use E or AUX to show all processes to get a sense for what's happening wholesale on the system. So PSEF is a similarly produced output showing the process, the owner, the PID, when it was started, and if it's connected to a pseudo terminal. And similarly PSAUX, but you get some additional columns including the percentage of the CPU and memory, vsize, virtual size, RSS, as well as stat, and so on. Most of these should be sleeping on even a busy system. They wake up when necessary and perform accordingly. So PS's purpose is to return to you information that is useful in the process listing table. You can grep, for example, for a particular user, and this will show you processes for that user or wherever the user's name appears, which generally will be for the first column. So PS as a non-privileged user shows the user's processes. Now what about as a privileged user? Let's SU in on this shell and run PS, and notice it also shows the processes that apply to the current shell for the current user. So that's how PS performs in this particular case. So let's drop the root shell, returning to the non-privileged user's shell so that we don't clobber anything unnecessarily. PS is a command that you'll use quite often to see which processes are running, in conjunction with who and W to see with whom the processes are associated. Now another command that's along the lines of PS is the top command. This is a dynamic PS listing. So dynamic PS because it updates frequently. Not only does it update the process listing, it also includes additional information from free as well as uptime. Now uptime we haven't covered. Free, before we go into top, shows you the amount of memory on the system, how much is in use, how much is free, how much of swap is allocated, and how much of swap is free or used. On a busy system, you may see some swap storage used, and that may be cause for concern with respect to the amount of physical memory that's available. It may mean that you have to retrofit your physical memory, meaning adding more physical memory to offset the swap usage. But indeed, because the system has 2 gigs of physical memory, it has double that of swap, as is the default installation mechanism. So free does that. Now uptime shows you how long the system has been up, and it shows you the number of users connected, 3 users, 3 shells. Each terminal creates a user, including the load average, 1515 minutes. And let's just include these additional commands that we've put into the mix. So free includes memory allocation, both RAM and swap, whereas uptime shows system uptime and load average. And as mentioned, top includes PS, free, and uptime. So let's run top to see what's happening. Now top by default will enumerate processes that belong to all users on the system. It shows you the processes that are consuming the majority of the resources, CPU, memory, and virtual memory as well. So CPU and memory being the important ones to measure, as well as virtual memory in the event that something's swapping too much. It also shows you the amount of time they're using the processor. Now above in the top output, notice it shows you the number of processes. There's a summary. So the number of tasks, the number running, the number sleeping, the number stopped, and the number zombied. This is a good sign that although there are 154 processes or tasks, the majority of them are sleeping. Only one happens to be running, and that one is possibly top in conjunction with GNOME, the graphical environment. Since we're moving around, we're using the mouse, we're doing things to cause GNOME to use CPU time. The remaining processes, many of them are background processes like SSH and otherwise, are sleeping. They're not servicing any requests currently. Then we also see the CPU utilization. This is VMstat. We should include that as well, that it includes VMstat output and memory breakdown from free, which includes swap. So 2 gigs of memory, roughly 450 megs in use, with the remainder 1.6 gigs roughly free, or 1.5 gigs roughly, 1.55 gigs or so. And the swap total, currently none in use, which means everything that the system needs to do is being done in memory. And then again, it arranges the output with the most busy processes towards the top of the list. Let's include that VMstat output is included for CPU utilization at any particular time, provided free of charge by the top command. So it's a good idea to have a console open with top running at all times to see which users, which processes are using the bulk of the resources on your system. Now let's move on. Not too much time on any particular tool, as we'll be referring to them throughout our studies. DF is a tool that shows the disk allocation. So the various mount points that are available will be enumerated when we execute DF. Now by default it shows the storage in kilobytes, which is why we use the H option, which returns in human readable, often in today's terms in gigabyte notation. So DF shows the partitions, including the tempfs partition, which is in memory, and the boot partition. It doesn't show swap, so it shows root, boot, and home, and it shows the size of each partition, percentage use or the amount use, percentage use, the amount available, and where in the tree this particular storage is mounted. So for example, the root file system is mounted at root. The boot file system, which is debsda1, is mounted at /boot, and home mounted at /home. So DF gives you a good sense as to how your storage is allocated, and so it shows this allocation and mount points so that you know what's mounted where, how your storage is spread, and percentage-wise where you stand, whether or not you need to make changes to the system. So a common way to run DF is with the human readable format. So human readable format. And we should just note that -H often means human readable for many commands. It's not always the case, but often is the case. So keep that in mind if in the event that your output shows information pertaining to memory and storage that seems a bit unintelligible or based on perhaps bytes or kilobytes, that you can use human readable to adjust the output. So some other things you can do. Oftentimes you simply want to take a look at your CPU configuration. if we cat from the virtual proc file system CPU info, and there are a number of files in there, but these are the common ones that I use, for example, which is why it's being referenced. Now there's a virtual file system named proc. Virtual in that it's in memory. The kernel maintains this file system when it's up and running and when your system is available. And it's dynamically or responsible for dynamically managing the contents of /proc as it's entirely in memory, which means the items are always changing, and many of them are 0 bytes because they change on the fly with new information. In there are various files that pertain to networking, storage configuration, and so on. CPU information can be quite important to look at from time to time just to see if you've rebooted and perhaps you've added processors, removed processors, or suspect that not all processors are available. Take a look at the CPU info file, and you see the various processors. So CPU 0, 3 gigahertz, P4, its cache size, so on and so forth. Spacebar through the page output. Here's processor 1. And this system appears to have 2 CPUs according to CPU info. If that matches your configuration, then you're fine. If not, you may need to check the configuration. Perhaps the kernel didn't detect the item. So enumerates detected CPUs that are running, of course, and are available. And let's just note that /proc is a virtual, and virtual means memory. So in memory, and in RAM in particular, FS, which houses system statistics. These are running statistics of your system, including memory configuration, networking, etc. CPU info is one of those. Another one is meminfo. In fact, just peruse the directory and you'll see a lot of files that are of interest, such as the whole net hierarchy, which explains your IP configuration or otherwise. So let's cat proc meminfo, and this returns detailed information about your system's memory. Total, and again, tools like free and top read directly from /proc. So let's just note that. Utilities or system utilities read from /proc to display settings or display values, i.e. free, top, etc. So here's a detailed display of our memory configuration. The total, 2 gigs, the amount that's currently free. When you run your command against meminfo, that's a snapshot in time. It's subject to change on subsequent runs. And if you pipe the output to less, you'll see whatever the new value is. And all of the specifics about the memory are displayed when you examine the meminfo file. And again, in proc, you'll find a number of files that pertain to various aspects of your system. There are also directories for the PIDs that are running on the system. So a number of items are in this directory. It's a very important directory, and it gives us a window into the kernel's behavior at any particular time. Take, for example, partitions. Let's see what's in partitions, and it shows us the partitions that are available. So major, minor, number of blocks in usage. This is the disk, SDA, SDA1, SDA2, DM, etc. VMstat, the version. Let's cat the version. Uptime, the version shows the kernel version, which uname, which is another command, shows. Uptime, which the kernel has to manage and changes dynamically, certainly not a fixed item. Swaps, swap configuration as it currently stands. It's a device that was generated automatically by the installation on this box. Zone info, which handles our configuration of our zone, and that dumps a lot of information. Piping it to less would do us better, and a number of other items. The proc directory is where you're going to find what the kernel is doing at any particular time. Oftentimes on a running Linux system, there isn't a need to interrogate this directory tree, but sometimes there is in the event of performance issues, such as memory overruns or debugs or crash dumps, will cause you to interrogate this directory to see what could be offhand. So catting prop CPU info and catting proc mem info will give you some useful information. Now let's move on. We mentioned that uname is a command. Enumerates kernel version. This is also important because sometimes there are discrepancies or unsupported items with or discrepancies between application support and kernel support. So you may have an application that's relegated to an older version or a specific version of a kernel. So it helps to have a handy way of displaying the kernel version. Uname in and of itself simply tells you you're running Linux. Uname is a command that's available across Unix and Linux distributions. So running it will return the OS that you're running. So this is Linux. Run it with help, and you'll see that the A option, which I like to run it with, will return all of these items. But you can return specific items like the processor, the hardware platform, by using any of these options. Uname-A just gets or cuts to the chase by returning everything. So here's the host name. That's this particular node's value, -n, according to uname. The kernel version, which is V, so you can pick it apart and put the variables that you'd like. So the kernel's version is listed as follows: when it was compiled, the platform, etc. So uname is good for returning that sort of information about the running kernel. And it's also stored in /proc, so you can reference it there. Now let's mention another useful nifty utility that you'll use from time to time to generate files for various usages, and we'll do it for doing little things like looping and scripting and so on. That's a sequence command. It generates a sequence of numbers, and this can be quite useful if you need to generate files for various items or to generate loops. Perhaps we'll just note that. So it generates a sequence of numbers, useful with looping in the shell, and we'll indicate shell as its variable, which of course expands to bash. And let's do a which seq. It's in user bin, and if you run it with no options, it tells you it needs some sort of option, such as a number to run up to. So sequence 10 generates 1 through 10. Sequence 210 generates 2 through 10. And similarly 27, 2 through 7. You can also influence the stepping. Running sequence help will show you the various options, but you can have it step at different values using the incrementer so that it increments at a value that makes sense for you. So sequence, let's say, start at 0, increment by 2, and stop at 10. We'll just give you those even numbers. Again, this can be quite useful for looping and performing n number of operations when used in conjunction with a for loop, for example, or just for generating files that contain n number of items or lines, for example. So I often like to generate files that contain, let's say, 1,000,000 entries by doing sequence 1,000,000 into, let's say, our home directory, which we've mentioned can be expanded using tilde, 1,000,000.txt. This gives us content to be able to copy and move around the place. And echoing the exit status shows 0, and LSLing with the human readable format tilde 1,000,000 text reveals its size. Now, of course, if we tail it, showing the last number from it, and that's 1,000,000 text, we'll see that it's 1,000,000. And conversely, if we head it using head and n1, then the first item is 1. Or perhaps heading the first 10 items will show numbers 1 through 10. So you get the idea. So sequence allows us to create very quickly a 6.6 megabyte file. You could also use DD if you'd like to generate files of specific sizes using perhaps a source such as dev0 to populate the file with zeros or otherwise. So there are a number of ways in which you can generate junk data for usage, perhaps for testing, network I/O, or otherwise. So far we've looked at a number of commands that are useful that you'll reference quite frequently. These are some key basic skills Linux commands. Time and time again they come up. And there are many, many other commands. This is by no means a comprehensive view, but rather a window into some of the more frequently referenced commands. With these commands, you can move around the system quite freely to get things done.